Okay, can you still hear me?
Yes, we hear you and we see the screen. It seems to work.
Great. And now the next test. Page up and down didn't work for me in a test I did yesterday. Let's see what happens. This is the title, of course, and we're only going to cover about a third of what's in here. So, hey, page up and down works. So we're in good shape. That's a relief. Anyway, you know me by now, and particularly through the Control Talk blog and the Control Talk column. We're going to go into three basic types of processes, and the most common process is the self-regulating process, and the idea here is if you put the controller in manual and you make a step change in the controller output, which is a delta %CO, that blue square that steps up, you would see for this direct acting process the process area %PV. If there's no disturbances, it would eventually come to a steady state. And I show percent signals because that's what the PID signals are for the PID algorithm. Very important to realize that. When you do a trend chart, of course, you're going to see this in engineering units. And there's usually a little bit of noise, so the time it takes to get out of the noise band is the observed total loop dead time. And I say that with a qualification that it does not include the effect of some things associated with a control valve, which is poor position or design, or some backlash and resolution limits. If your idea here is to make a step change large enough to get through those things and to study what the process is doing. So this total loop dead time does not have the effect of backlash, resolution limits, or poor position or design. Once it gets out of the noise band, and then it gets into the exponential response, and since this process has a negative feedback time constant, that's good. It means that it is self-regulating and that it will come to a new steady state, provided there are no more disturbances. And the change in process variable in percent divided by the change in controller output in percent is the open loop self-regulating process gain. And its units are percent divided by percent, so it's dimensionless. And this is very important to make sure if you compute any process gains that for PID tuning, that for the steady state gain, that you make sure that you end up with it being dimensionless. If it isn't, you've got something missing in terms of what you're doing in terms of computing that open loop self-regulating process gain. And it's kind of interesting. I've kept adding more words to that description to help understand, and that first of all, it is open loop. The test is done with the controller manual. It's a self-regulating process, and is what we're looking at. So that's all in there. And then, of course, it is a gain that we're interested in here. There's also a time constant, and it is the open loop time constant, and it's the largest time constant in the loop. Ideally, we want it to be in the process, but it doesn't necessarily end up being that way, and we'll get into that. The controller doesn't know where it is. It just knows there is a big time constant, so in this first order plus dead time approximation, and by first order it means we have a single time constant we're focusing on, the largest time constant, and everything else is effectively dead time. And then we have this open loop self-regulating process gain. That's the first order response that we're using as an approximation here. Now, a second order response would try and identify the second largest time constant as well. If the time constant, the largest time constant in the loop is greater than 4 times the dead time, it is classified as near integrating. And I didn't realize how important this was until I started to try and look at tuning loops, and particularly using lambda tuning. And they did, Bilkowski, like 10, 20 years ago, did mention this, but he didn't say when you needed to do this switch to a near integrating process. And I kind of found that if you want to get settings similar to what's typically out there, and I think what we saw from Michel Ruel and also from Shinsky, and you're using lambda tuning, it's important that you switch to tuning rules for a near integrating process. And the logic is this, and that the PID, what it is seeing in like 4 dead times, which is the time we normally associate with seeing most of the PID action, unless we have deliberately detuned it, occurs in those 4 dead times. And in that 4 dead times, if the time constant is larger than that, what it appears to the controller is that there's a ramp going on, and it doesn't know that it's eventually going to reach a steady state. It sees the ramp, and so we tune it based on that, and that has helped lambda tuning. I expect it would help internal model control and Skudstad's internal model control tuning as well, although I haven't kept up with either one of those internal model control tuning settings and actually all the modifications that sometimes been proposed to know if anybody is advocating this. We just know we need to advocate it when we use lambda tuning. And it's also, I think, interesting in terms of analysis and understanding things. And sometimes software uses this understanding. So in near integrating, it looks like a ramp in the time frame of the PID response, which is 4 dead times. The equivalent open loop integrating process gain is equal to this steady state process gain divided by the largest open loop time constant there. And we hope it's in the process, but it's not necessarily that case. Now, is that integrating process gain small or large? Well, it turns out for some temperature processes, it's usually quite small. But if you talk about pH, where the steady state process gain is quite large through the titration curve, the steep slope, you can end up with a very fast integrating process gain. It depends not only, as shown here, on the time constant, but also on the open loop steady state gain. And this is kind of a neat formula because it allows you to convert back and forth between them. And I think like decades ago, when they really weren't into understanding how to tune for integrating processes, they would take an integrating process and equate it back through this simple equation to a self-regulating process, so they could use their tuning rules. And there they probably would just say, oh, well, let's, for this equivalent self-regulating process, we'll just say the process gain is 1, and we're trying to get tuning settings based on that. And it did work. So this equation has been around for many decades. Now, a true integrating process response doesn't reach a steady state when the controller is in manual. It just continues ramping. Of course, there's some physical limit. This classical integrating process is a level process, and of course, the tank can run dry or it can overflow, or if you're talking about pressure, it's even worse. I mean, you can see the pressure limits of the vessel or column, and there's a relief valve or rupture disc that can blow. And you can also create vacuum and suck vessels in. So pressure being a ramping situation, tending to be a ramping situation, is also an important integrating process. Well, it turns out in pressure it may not be true integrating, but that's a finer point we can get into. With level, unless you have gravity flow, With level we're talking about a pump discharge usually. We have a true integrating process there where we have a ramp rate. And if we're going to do a test, an open loop test, what we got to realize, since it always tends to ramp, it may be ramping in one direction or the other when we start the test. I mean, if we're really lucky and it's lined out and right away we start the test as soon as we put it in menu, it may not be much of a ramp in one direction or the other. But here I show that you need to take that into account, and really the integrating process gain is the change in ramp rates that we see. And again, we're dealing with percent PVs, so it's percent per second ramp rate, and we're looking at the change in ramp rates, and we're dividing that by the percent controller output. And we end up with an open loop integrating process gain whose units are percent per second ramp rate divided by percent change in controller output. And typically, you don't see this detail. They cancel out the percents, and what they say for the open loop integrating process gain is 1/seconds. And as I mentioned, for temperatures and levels, it could be 10 to the -6, 1/seconds. But and that's for large vessels or large columns, and but for some other things, like some pressures, like in a phosphorus furnace pressures, where they make phosphorus with an electrical furnace, the pressure could ramp off scale in a few seconds. And then there was an incinerator I worked on, and it was incredibly fast. It was so fast we had to use analog controllers. We couldn't. It was too slow to use a digital controller. And all we know, in either of those cases, you really couldn't put the controller in manual. I did some calculations, based on physical principles, and found that that particular incinerator, the pressure could ramp off scale in 1/4 second. Which explained a lot of the problems we were seeing. So anyway, there's a large diversity of ramp rates. Often the ones we see, though, for temperature and for composition other than pH, the ramp rates are quite slow. Then we have a runaway process response. Hopefully you never see these. Unfortunately, in my career early on, well, fortunately and unfortunately, I mean, there was never an incident, but I was in the control room when they said, well, yeah, it's reached the point of no return, the polymerization reactor, and it's going to blow, and they meant it was going to blow over to the relief, blow through relief to the flare stack system, which it did. We try not to design processes to ever be a runaway, but some polymerization processes have such a high rate of reaction in terms of how it increases as the temperature increases that it can occur. And there was a number of these polymerization batch reactors in Monsanto, and the concern was so great there that they didn't allow integral action. They only used proportional and derivative action, which brings me to a point I didn't mention when you're talking about integrating processes. There's no internal feedback within the process; it just ramps. So here we're talking about the internal feedback being positive. There's a positive feedback time constant, and when you don't have the negative feedback in a process, the way you achieve that is by having a more gain action, more proportional action. And it becomes important, as we'll see, in near integrating even, and that was part of the enlightenment that occurred with going to a near integrating approximation, which we'll see in part 2 of this WebEx Mentor series. It's so important, and you can kind of visualize this in that if you have an integrating process and you have a high gain and you make a step change, it'll line out with an offset, but it adds the missing self-regulation. So the proportional gain action adds the negative feedback that's missing in the process. So here we get to the runaway. It becomes even more important that we have this gain action from the PID, and there's actually a window of allowable PID gains Lieben documented in some articles, 20 or more years ago, and it showed that, besides being a maximum PID gain, we all understand that too much of a PID gain causes excessive oscillations. He said that for runaway processes, these runaway reactors, typically polymerization reactors, we get into a situation where there's too low a PID gain, and it's just going to run away from you due to not enough negative feedback added by the proportional mode to make up for the positive feedback in the process. And he quantified how that ratio of the maximum possible gain and the minimum possible gain, how the ratio changed with heat transfer surface lags and thermal well lags. And he did it only for proportional plus derivative controller. He didn't even put reset action, which kind of, maybe that's, we had really good reasons why we didn't want to put reset action in there. Now you can if you do it very cautiously, but really, reset action, as we get into the very last of these mental WebEx, we see that the kind of a clue here is the way you implement integral action and the way it was done originally and the way it's still done in many systems that have the greatest capability that we're going to get into here in terms of external reset feedback. The integral mode is actually implemented with a positive feedback. So here you can say, hey, I've got positive feedback in the process. I add integral action, which is implemented with a positive feedback methodology. You can see, that can be problematic. Now, fortunately, most people never see this acceleration, and you would never do a test to see this acceleration because it would be dangerous. So tests are terminated before that happens, and you can't put these controllers in manual for very long, if at all. And so that you have to do tests where the controller stays in automatic by making set point changes. And it turns out for these type processes, hopefully the time constant, primary time constant, is so large that it is so slow that you can use a large PID gain. And as a result, you can do a test in automatic and make a set point change, and you're going to get a step change in controller output, assuming the structure has a proportional action on error, and you can identify the dynamics of that, what's happening there with the controller staying in automatic, at least in terms of the dead time and the ramp rate. We tend to never even try and measure this acceleration. We treat this as an integrating process with our tuning rules. And if you really want to get into when this acceleration does occur for what process designs, you would look at the different ordinary differential equations I have in Appendix F and I think it's Appendix F in many of my books. Many of my books have that appendix which has the ordinary differential equations that will show when you get into a reaction rate heat release that's a function of temperature that exceeds the cooling capability and causes a positive feedback action, and you can actually estimate. And in fact, that's the only way really of getting an idea. You can't measure this online. The only thing you can do is from the ordinary differential equations estimate what it is based on first principles. So examples, near integrating processes. Continuous column composition and temperature control. And that's saying they're integrating because the time constant is greater than 4 times the dead time. Typically for columns, if we're looking at the liquid response in the column, it's maybe 5 to 6 time constants, process time constant, 5 to 6 times the dead time, I believe. Continuous vessel composition and temperature control. And here, for crystallized evaporators, fermenters, neutralizer reactor, here we're talking about much larger ratios, maybe a ratio of 100 to 1 or even more for a well-mixed vessel, which we get into particularly for reactors. And then there's the true integrating processes. And level being the classic, the ramp rate of the level increase is the inflow minus the outflow. Then batch column composition, pressure, and temperature control. And while it may not truly be integrating if you look at this as with the equations, but it turns out for practical matters, it is, and that you would never want to get to the point where you've pushed the limits associated with it finally seeing sort of a steady state. It would be way beyond the pressure and temperature or limits that you have. And similarly, we have a batch vessel composition, pressure, and temperature control for crystallizers, evaporators, fermenters, neutralizers, and reactors again. And then the runaway process. Well, the classic is polymerization reactor control, where it's highly exothermic. Then we have some things that really are not so much out there. We have biological reactors. If you were looking at the exponential growth phase, and you're actually doing closed loop cell concentration control, there could be this acceleration going on. But the fact of the matter is, I haven't seen that closed loop control, and the growth rate is so slow. I mean, particularly we're talking about mammalian cell reactors. They take a couple of weeks for the batch, and it's so slow that really you're not concerned and don't really see that acceleration in terms of the time frame that you're dealing with. So it's more of an academic view. I have seen the actual compressor speed control acceleration. In fact, my early introduction to compressors many decades ago was this axial compressor that would accelerate at the start of surge and would damage itself in less than a second. And we found out the only way we could protect this compressor was to put in a derivative module that looked at the derivative of speed and would shut down the compressor within maybe a tenth of a second or less and it had to be an analog type device detecting the acceleration in the compressor speed. And that may have been a very special axial compressors, although axial compressors tend to be the most problematic in terms of their reaction to surge, in terms of their extreme response, and also the damage that can occur. Now, strong acid and base pH control, as you approach the neutral point, it's accelerating. And the PID controller sees that, and it doesn't know that, hey, once you get past the neutralization point, it's going to slow down. You just have to recognize that, what the PID sees is what you need to address in the tuning. And so the tuning, if you're, say, at a 4 or 5 pH and it can accelerate to 7 pH, you need to be kind of aggressive again with the proportional action and derivative action to help prevent that acceleration. Okay, there's quite a bit of disagreement out there, I've noticed over the years, and I came out of one world, but there's many other worlds in process control, and so it's always been interesting to me to kind of expand my horizons and to understand where other people are coming from. So one of the key things to recognize that is not commonly discussed is and there's different terms used for this, but I like the term final resting value, and I think I got that from model predictive control. That's a term they use. But anyway, after you have a disturbance and the controller output is lined out, what value is that lined out at after it's dealt with the disturbance or the set point change? And so it's the final resting value of the PID output, and so we're going to use the acronym FRV, which you've probably never seen anywhere else but in my publications. So when I was at Monsanto doing applications, I was concerned about minimizing the peak error in the load response, and I was concerned about that to prevent compressor surge, safety instrumentated system activation, relief valve activation, triggering undesirable reactions, and in bioreactors, poor cell health. They're very sensitive, particularly in mammalian cells, to pH and temperature. But what you tend to see in the literature is a minimum PV integrated error in the load or set point response, and often it's actually the integrated absolute error. Hopefully your oscillations are not crossing set point, in which case, or if they are crossing, it's very little. It's settling down pretty soon after crossing set point. Then whether it's integrated error or integrated absolute error doesn't really matter. But this is what's in the literature typically, and I can equate it to the total amount of off-spec product that enables, you want to minimize that to enable closer operation to an optimum set point. Then there's other things, like minimum PV overshoot of the set point and the set point response, prevent compressor surge, SIS activation, relief, undesirable reactions, and poor cell health. In fact, for bioreactors, it's very extreme. I didn't realize it. I was very proud that I had reduced the temperature overshoot to like 1 to 2/10 of a degree centigrade, and the biochemist was still unhappy with it. That was too much of an overshoot in temperature. And I have had some, and I think this is a little extreme, but some statements have been made that overshoots of pH of 0.02 pH is unhealthy. I think that it's hard to even measure that reasonably. So maybe it could be more like 0.04, 0.05 pH, but still an extreme sensitivity to overshoot. And they make set point changes in bioreactors in pH and temperature to move from promoting cell growth to promoting product formation. And they call these temperature shifts or pH shifts going on. And when they make them, and they don't care how long it takes to get there, but they don't want any overshoot. Don't want any overshoot. And of course, in startup, they got to get it to operating temperature. Don't care how long it gets there, but no overshoot. You don't want like too high temperature, particularly, is going to kill cells very rapidly. And then there's this thing I didn't even realize was out there until I read an article in hydrocarbon processing where this very well-known author and frequent contributor to hydrocarbon processing was saying the main loop objective is the minimum output overshoot of the final resting value in the set point response. And not only was it like saying, oh, this is the only thing, but he was kind of making fun of people who thought elsewise. And there's a legitimate need for that in hydrocarbon processes due to some interaction with heat integration, recycle loops in these gas unit operations. Now, I'm not familiar enough with that to know the details. I do know that's one of the reasons why they go to model predictive control, because of the complex dynamics and delayed reactions going on. But you got to realize, while that may be valid for those type of unit operations, it can be dangerous for others. And so I got Michel Ruel and I think another guy to help me do a few control talk blogs, because I just didn't want me saying this. I even got Shinsky involved, and we did a few control talk blogs saying, you can't say unequivocally that your objective in control loops is to minimize the overshoot of the final resting value, and because it would be downright dangerous. Well, you can't. It's not possible in integrating loops, and really not even feasible in near integrating loops, and it's very dangerous in runaway loops. Then there's another objective: minimum PV time to reach set point and set point response, minimize batch cycle time, startup time, transition time to new products and operating states. And this was important for me because my chemical batches, where I did most of the work before working in bioreactors, the chemical batch cycle times were like maybe 4 hours. And if I were to save 25 minutes on reaching set point, as they got to the initial operating point, or maybe as they changed it at some point in the batch, I saved 25 minutes. I could reduce the batch cycle time by 10%, and if the batch processing capability downstream could handle it, I increased the process capacity by 10%. So for me, the minimum PV time to reach set point and set point response was important, but that's not the case for, certainly not for bioreactors, because like I say, from a million cells, it may take 2 weeks. And if it takes 25 more minutes to reach that point, that's inconsequential in terms of batch cycle time. In fact, their holding batch is much longer than probably they need to, so there's probably more opportunity there. And this is something I've added in that you don't see out there: minimum split range crossings to prevent wasted energy, reactants, reagents. Split range, we're often talking about heating, cooling. If you go back and forth between heating and cooling, you're wasting energy. Similarly, if you have pH control and you have split range between acid and base, you're going back and forth between the acid and base, then you're wasting reagent. And in terms of cell health, particularly mammalian cells, because the two reagents are carbon dioxide to give you carbonic acid, and sodium bicarbonate act as a base. If you start oscillating back and forth, and it's very prone to happen because the reagent demand is pretty small, you end up then with building up your sodium concentration, and this high sodium concentration causes a high osmotic pressure in the cells, causes their membranes to break, and eventually rupture, so it causes cell death. So we want to minimize those split range crossings. Then there's something that is very prevalent and very important, and that is, it's more commonly, well, how do you control the surge tank level? And it turns out, if you look at processes, whether it's surge tank level or some other level, where you really don't need tight control of the level, but you want to minimize how much it's manipulating a flow, because that flow, typically being a discharge flow, is upsetting other unit operations downstream. And you're changing the feed to them. And it's interesting that some studies come down to, and they say, where are these oscillations coming in this plant? Well, they trace it all back to a level controller. And so the term used here is maximum absorption of variability and level. And really what it is loose level control. But hopefully non-oscillatory loose level control, and that's where we'll get into where we need to be careful. How we try and achieve loose level control, and that will be in part 2. Just give you a heads up. If you decrease the PID gain, you get into these slow oscillations. Really what you need to do is make sure that the reset time is very large, and then you can decrease the controller gain. But we have relationships to show that, and we can show you the consequences next month, and also the equations for those relationships. So to maximize the absorption of variability, what we're trying to do, we're trying to minimize the passing of changes in input flows to output flows that are upsetting downstream unit operations. Another way that I looked at it originally as minimizing the transfer of variability from the controlled variable to the manipulated variable. And then that's the subject I added in here. There's this general thing with control loops where we need to optimize the transfer of variability from the controlled to the manipulated variable. However, it sounds much better to say maximize the absorption of variability rather than to say minimize the transfer of variability from the controlled to manipulated variable. So I can understand why that term maximum absorption of variability is used. But I like to put it in this context of the greater overview of what we're trying to do. Control loops don't make variability disappear right there in the control loop. What they do is they transfer it from something you want to stay at set point to something that you have freedom to move. And so you're transferring variability from the control variable to keep it at set point to a manipulated variable. And how you do that changes depending upon your loop objectives that we've been talking about here. Now, you will see variability disappear in the process variable as a result of the attenuation action that you get from backmixed volumes that smooth out the oscillation. So, yeah, the process can reduce what you see as variability, but that depends upon having volumes that have some mixing going on, so that these volumes kind of, like a filter. If you're coming from an electronic world, it's that resonance time and that volume that's got mixing is the filter time constant. And so if you have oscillations going on, that filter time constant can attenuate them, and so you don't see them. And I, working with mostly with vessels and columns, sometimes I was told, well, yeah, I don't see the value of what you're going to be doing, because, for example, on a distillation column, they had a valve due to backlash and stiction. I think it was due to stiction, was causing an oscillation in the reflux flow. And I said, well, gee, you got to get a better valve. Well, it turns out with the volume in that distillation column, I couldn't see the oscillation in the product composition. And that is something I've kind of focused on, and that's part of the fact that we have different worlds. In hydrocarbon processes and other gas unit operation with plug flow and heat integration recycle streams, crackers, furnaces, and reformers, and I don't know that much about this world, although I have worked on some hydrogen reformers, and of course I've worked on some furnaces. They have a fast self-regulating responses, interactions, complex secondary responses with sensitivity of set point and FRV overshoot plus split range crossings and utility interactions. So you can see how their emphasis is less on having proportional action and more on having integral action. Of course, they don't need the proportional action because they don't have this missing self-regulation. Plus, if you do an immediate response and there's interactions or secondary things that are happening due to recycle and heat integration going on, taking an immediate reaction is not right. You need more patience and take a slower, more gradual action, which is what you get with interval action. Chemical batch and continuous processes with vessels and columns, it's important that loops tend to have slow, near, or true integrating runaway responses. And this is the world I primarily came from. And we wanted to minimize the peak and integrated errors and rise time as key objectives. Utility systems. I worked on some of these. It's important to have fast, near, or true integrating response with a minimized peak and integrated errors and interactions as key objectives. And then on this next one, and I grouped this together, I don't know whether this is truly a good grouping or not, but I was running out of space. But I tended to put the fast self-regulating process of inline systems where the process time constant, if you're not talking about heat transfer, is pretty small, and so you have a fast self-regulating process, and this occurs for some inline composition controls, whether static mixers or there are other inline operations with pulp and operate units. Then there's extrusion, and I have some experience because Monsanto was a big, and then Solutia, a big, maybe the world's largest producer of safety sheet liners that go into windshields and safety glass. Anyway, so the extrusion and sheet processes there have very little time constant. In fact, the sheet process itself has none if the die bolts are actuated. Now, if the die bolts, if the gap there is changing due to heat transfer, which is the case we had for the plastic sheets, then you do have a time constant associated with the manipulation through heat transfer of those die bolts. But these are fast self-regulating processes in the interaction, the propagation of variability into the product. There's little to no attenuation of these oscillations by back mixed volumes. There are, of course, exceptions to any sort of generalities I'm saying here, with extreme sensitivity, variability, and resonance. Loops, particularly for sheets, can be dead time dominant due to transportation delays unless there are heat transfer lags. So there's a very sensitivity, and this is where lambda tuning came from, I think, with pulp and paper. Very extreme sensitivity to minimizing variability because it was propagating downstream. It wasn't being attenuated by back mixed volumes, and it was showing up in the sheets. And so the emphasis was more on more gradual action with more integral mode. Biological vessels, fermenters, bioreactors, the most important loops tend to have slower near true integrating response with extreme sensitivity to set point and FRV overshoot, split range crossings, utility interaction. And the other thing is the load disturbances originating from the cells are incredibly slow. So, you don't even get into peak errors being a concern because the rate of change of the disturbance is so slow. Even if the controller is not tuned very aggressively or tuned very sluggishly, it still can deal with the load disturbances. Okay, I like this block diagram. It may be a little bit overwhelming at first, and it doesn't even show all the dynamics in a control loop. But I like to at least get people oriented to the fact that what's really there requires more attention than what perhaps we tend to get seen in the literature. In the literature, they tend to say there is a process gain and a process time constant and a process dead time. Well, I like to say that there is an open loop gain, and it can be a self-regulating process or near integrating or true integrating process gain, and there is a total loop dead time and an open loop time constant. Now, the open loop time constant is the largest time constant in this block diagram. Hopefully, it's the primary lag, and so I'm using the short notation here of lag for time constant and delay for dead time. And so we hope that the largest time constant is the primary lag, which is what's shown in the process here. And in the vessels and columns I worked with, the disturbances entered at the input to the process. And so having a large primary lag slowed down what the disturbance would cause in terms of an excursion, giving time for the PID controller to catch up with it. Furthermore, if we get into the tuning rules, it ends up that this large primary lag with respect to the dead time enables a very high controller gain, which is very important for near integrating, and runaway processes. So this is what you want. And so people would say, oh, that process is not good because it's slow. And I say, well, where is it slow? If it's slow because of a large primary lag, I really like that because and if my load disturbances are coming on the input. Now, what's interesting in the literature, and I think particularly for internal model control, they showed the disturbance on the output of the process, not the input of the process. And so it bypassed this primary lag. So they didn't see the advantage in terms of the primary lag, in terms of its slowing down disturbances. And Shinsky really took a big objection to this. And it's one of the sources of disagreement out there. And that's what I was trying to resolve by going to the near integrating approach and tuning rules to make them come together. And also we'll see, to set lambda not as a factor of a time constant, but as a dead time, like, maybe 2 dead times, 3 dead times. And it kind of unifies the tuning methods, and we can get on a similar basis. Now, if you have a very small, relatively small primary lag here, it doesn't matter too much where that disturbance comes in, whether it's on the input of the process, the output of the process. So for some pulp and paper processes, it really didn't matter whether they showed, I think, the disturbance coming on the input or the output. And it is really, I think, the primary source of disagreement. So the disagreement kind of goes away if the primary lag is small, and we're talking about fast self-regulating processes. And we only get into like problems with internal model control and lambda tuning rules if we get into large primary lags. But we can resolve that, and that's one of the objectives I've had, to make us more aware. And there are some benefits, I think, that will show furthermore by thinking of the near integrating processes. There's many time constants here. So you find the largest time constant, and that's your open loop time constant, and you then say any of the other small time constants are converted to dead time. And this is something that was started way back in the 1940s by Ziegler and Nichols, and they take a lot of flack for their tuning methods being very aggressive, but they did an extraordinary thing there in terms of our understanding, and you can approximate how much of that smaller time constant is converted to dead time by the graphs that they created, and that fraction varies from 0.28 to 0.88 for ratios that go from 1 to 0.01 respectively. And so what you want to do in a first order approximation, as shown in the bottom here, is to sum up all the pure dead times and then apply these Y factors to each of the small time constants, and you get the total dead time. And you can see it gets complicated. It can originate in the valve and the measurement. The valve is particularly problematic. If you've seen my article on valve response that was in Control magazine, it is incredibly complex and variable, and and problems caused by poor positioners and poor actuators and poor valve designs is just incredible. And not only in terms of the dead time, but the variability in that dead time. So it's important to realize that these delays can originate anywhere, and for flow and liquid pressure processes, often the primary lag and the secondary lag in the process is smaller than what the measurement lag is, or if you put a filter in the controller, so it becomes very problematic, or what the valve is doing in terms of its response, which is especially difficult since it's so difficult to estimate what that lag is in the valve. And that's a whole topic in itself. So we're going to stop right here and continue on with this in part 2 next month. Here, just give you a preview. We're looking at the response of a PID controller to a set point change or a structure PID on error. And I'm going to send out the file, and so if you have some time, you can kind of look ahead as to where we're going, and you can look back at what we've done. So I'm going to, at this point, return. And hopefully you guys are not worn out. And as usual, I had maybe more material than you probably could absorb all at once. Any questions?
Yes, great. When you were talking about the runaway processes, and we're also mentioning that it will be probably not desired having the loop or make step changes where the control loop is not in control. Is the closed loop tuning method recommended way of tuning? Is it reliable?
It is more difficult, and there's, I think for runaway processes and for some of those furnaces I mentioned that could ramp off scale, you have no alternative, and there are several different closed loop methods. Actually, the relay method, even though it's very unpopular, relay oscillation method, if you choose the right step size, will keep crossing the set point and come up with the tuning settings. The other method, of course, was originated from Ziegler-Nichols, but I've modified it in saying you never really want to go for ultimate oscillations. You just want to get some oscillations, and then you measure the period and you to get an idea of what the reset time is, and you're probably going to end up with a larger reset time, but that's probably good, and then you cut the gain more and you test it again. But then there's another method, and people can keep the controller in automatic, and they can make a set point change. And if the tuning is such that it has a lot of proportional action, I can develop a calculation that will identify it. But I'm sure there's software out there that can, for set point changes, identify the dynamics. And then there's another option, which I didn't mention. This is what Shinsky says, you momentarily, and this is a trick, I guess, for the furnaces that couldn't do that because it wasn't fast enough unless this would be done programmatically. But if you put the controller in manual for a second and make the output change, and I'm kind of thinking, it could be a few seconds for a lot of cases, but for those furnaces, it would have to be a fraction of a second. You make an output change, you put it right back into auto. You can see what the response is. But I think the software today can handle do identification from set point changes. They can also inject output changes with the controller in automatic, and so you don't have to put the controller manual to get these classical responses that I showed in those slides. Michelle, you want to comment on that? Because I know you've been working.
Greg saying that, yes, with the tools we have today, we can be in auto, and we will just add a jitter signal on the set point. So very small changes, very quick changes. And we will be able to capture the model if it's integrating or runaway. We will be able to capture the model very quickly. And the main point is you remain near set point. You don't move away from set point.
Right. Yeah. And you know, my familiarity with the relay oscillation method was actually you do it right. You know, the oscillations across set point are very tiny. In fact, you got to make sure that if you want to see them, that you zoom in on them to look at them. But yeah, I think in general the tools today allow you to do these tests in automatic, and I think the manual tests are mostly if you're trying to understand what's going on just manually. Yeah.
Okay.
Yeah, good question. Again,
Greg, I would like to add on your slide number 8.
Okay.
I think you should add something about what I call physical processes like mining and metallurgy. In mining, especially, you have a lot of control loops which are from crushers or mills or conveyors, where the signal is very noisy. You have most of the time they are self-integrating, but the challenge is the equipment and the measurement. You have a lack of sensors in many variables, so it's a different animal.
Yeah, definitely. And in fact, I did a couple of control talk columns on control in the mining industry, and you're right. It's a different world with really special problems, challenges, I guess you say. Yeah, that's a good point. Yeah, I'll have to add that here, and I have to probably make the type smaller.
That's a real estate problem on that slide.
Yeah, it is. And I'm sure I'm leaving out some processes of people that their world is that's their career, and I don't really do much for food, and I do have a friend from Monsanto who ended up at Ralston Purina, and he says it is so different, and he's kind of disappointed that actually ISA doesn't really address what their concerns and needs are in the food industry. Dog food, pet food, I should say. Yeah.
Yeah, well, I have another question, but I don't know how we are doing about timing.
It's okay. I got time. And people can just sign off. I understand you got constraints, so just so you know, if you have to go ahead and go.
In your next slide. Okay. I have always been intrigued by the secondary lag, or what it is called as the secondary time constant, which I think is the one you're showing there of the secondary lag.
Yes.
And I've seen that the secondary lag is what you will enter as the rate time.
Yes.
Something like the lambda. So I'm wondering, how is that you differentiate from the primary lag versus the secondary lag, and how did you get to identify it or measure it? Is that a change in the slope when you are working with integrating processes?
Yeah, there's software that will do that. Let me say this, and some tuning methods focus on that, and if the secondary lag comes often from heat transfer and sometimes from mixing, but principally from heat transfer lags, heat transfer surfaces. lambda tuning focuses on that. And I've been shown their test cases where, they show, hey, where the secondary lag was quite large compared to the dead time. And they show how much better, lambda tuning is than other tuning methods. Well, if you made a first-order approximation and took that secondary lag as dead time, then you wouldn't, you would have increased your rate time, and you wouldn't see the big benefit. And then there can be situations where there's both a large dead time and a large secondary lag. And so what I did was I modified my lambda equations to take into account both the secondary lag and the dead time, and in terms of the rate action. And this keeps you out of trouble in that if there's that if you don't have much of a secondary lag or you haven't identified it, you still get the rate action you need, and it just makes more sense to me to resolve this difference that's out there, and people saying, well, this tuning method is much better than another tuning method, and they come up with a case. And really, you can probably modify most tuning methods to deal with these cases that they're talking about, and you also should realize there are other cases. Now, saying all that, we can go back and, there must be another way of doing this, but here, if we look at the fact that in the beginning of the response, right after the dead time, it doesn't come up as a straight ramp in a true first order, but there's a bend. That initial bend is due to the secondary time constant, whether it's here or to a less extent and not so visible there, but also visible here. And so that initial bend is the secondary time constant. And if it was only if you only had one time constant, a primary time constant, there would almost be what looked like a straight line coming down to where the noise band is, and you wouldn't see that initial bend going on. Software can identify that. I remember, decades ago that some guy discounted how important that was, but he was using tuning rules that would add derivative action based on dead time, where the lambda tuning rules will not add any derivative action based on dead time. You have to have a secondary time constant. So if you don't identify it, you're out of luck in terms of derivative action on the slow process.
Okay.
Very good question, because I've seen those cases presented, and honestly, I didn't take the time to argue about it, but I thought through them and realized, you could present a case where the dead time was large and the secondary time constant was not, and then, the conclusions were the opposite of what they were as well as the value of lambda tuning versus conventional tuning rules that don't set the derivative action based on secondary time constant. It requires greater sophistication to identify the secondary time constant. And Michelle, I guess the software you have, I think most software today will identify that. Is that true for your software you work with?
Yes, but I agree with you that you can, for the sake of understanding the process, you can simplify first order and dead time. And if you have a second time constant, you just reduce your dead time, and at the end of the day, if you play with the numbers a little bit, you will see that there is no much gain to find that second time constant.
Yeah, I agree with that, that's why I like conversations where we try and come together instead of saying, oh, you got to do it this way, or this is the only way. I like to get a bigger perspective and a bigger understanding, because I think it leads dealing with ability to deal with so many more different types of situations, which it's incredible in the process industry. As I tried to show you there with the different worlds, the different situations. So you need a kind of a bigger perspective so that you don't narrow your conclusions based on where you primarily worked in, what applications you worked in.
Coming back to all the distinction between lambda tuning and lambda tuning for near integrating process, which are in fact two different animals, which are two different sets of formulas. It's coming mostly from in the computer industry. They like to look at set point change, not load change.
Right.
And really the lambda tuning rule was developed to, I would say, nice landing, not nice takeoff. So if you look at the lambda tuning rule for self-regulating processes, really the rule was developed to have a nice set point change. And the near integrating process, the rule was developed to stop the disturbance and stop going back to set point. So in one case, you are like taking off, and in the other case, you are landing. So it's really different, and even if the name is the same for lambda self-regulating and lambda near integrating, the goal was different from the beginning.
That's right, and that was one of the benefits I saw switching to near integrating rules. I was concerned about load disturbance rejection in my processes and the tuning to take advantage of that. And really that's what the lambda becomes an arrest time. And
exactly.
And so it's saying, you know, how long does it take for you to turn around that response to stop deviating and to start to return to set point? Yeah, that's a critical thing, and so that was the other aspect of it. And then it turns out that for fast self-regulating processes, there are refinements you can make, but it turns out that because of the time constant there, whether you're being relatively small primary time constant, whether you're tuning for load disturbances or tuning for set point changes, that it's not that important. Although I think what you really want to do is kind of think, well, and we'll get into this, but lambda should not be set in terms of a close loop time constant or an open loop time constant. You should set lambda as a dead time, and then the tuning methods converge, and you get a good load rejection response as well as a set point response. And we'll get into this, that actually what Shinsky would say, and many others in his thinking would say, that you want to tune for load disturbances, because if we didn't have load disturbances, why would we need control loops, really? But you have the load disturbance, you want to address that first. And you can get the set point response you want, which we'll see by the use of different PID options, like PID structure. And he would say putting a lead lag on the set point. But so you can tune for load disturbance and then still achieve the desired set point response in terms of minimizing overshoot by some use of PID options.
Hey, Greg, I have to go, so thank you very much.
Thank you.
The next one will be fun too.
All right, great. Look forward to it. All right, this went pretty smooth. We should have a great recording, and I'll send that out. Well, I won't send it out. It's too big. It'll be posted by ISA, and I'll let you know. I'll send you the link.
Good.
Thank you, Greg.
Okay, thanks. Thanks, guys.